Video, I'd like to explain the concept of big O notation, which is used to describe mathematical and computational algorithms um, and their complexity. And it's often something that is very confusing for first time uh, for people when they first come across this concept. So let me kind of give you the definition first. I pretty much just said it. Big O notation is used to describe the rate of growth um, of the running of an algorithm. Typically, Big O is the worst case scenario or the longest time it would take to run that certain bit of code or the mathematical function. N is usually used to describe the size. For example, if you're looking at an array or a list of um, data, if it has 12 items, that this array actually has 12 items in it, we would say that the N for that is 12, since there are 12 items in that. If you're running a sequential search on this array, the big O would be O of N, since the worst case scenario is that it would take N searches for you to find the item you're looking for. And for those of you who aren't familiar with what a sequential search is, so we have this, your array here of numbers, and let's say you're looking for 31. This code here, which is done in Java code, will look at every element in starting with the first spot, or spot 0 for that matter, and go through each one until it finds the number, in this case 31, that you're looking for. So you can see how the worst case scenario for this would be N, 12, because if it doesn't exist, or the number you're looking for is 45, you're going to have to look through this 12 times. So that's how you come up with a big O of 12 for this, for the worst case scenario. Best case scenario is big O of 1, because if you're looking for, let's say, the number 1, then you're going to find it your first time through. So the 1 refers to the number of times needed to find it. All right. So 90% of the time when you come across and talk about big O, you're talking about big O in the worst case scenario. But you may see the omega sign is sometimes referred to as the big omega, and it's used to represent the best case scenario of an algorithm. So the omega is, for our last scenario, would be 1, because in the best case scenario, you only have to search through it one and look at one element in that array, and you found what you were looking for, right? The theta is, and these are Greek letters if you're not familiar with them, is used to represent the average scenario. This one does not get talked about this one gets talked about even less so than the omega, and both of them are traditionally not really mentioned too much. The big O is typically the one you talk about. But in our previous example, the average scenario would most likely be N divided by 2, because for most scenarios, it's going to happen somewhere in between 0 and N that you'll find the item you're looking for. All right. So that's those terms there which you may come across from time to time. So this is a nice chart provided by thebigocheatsheet.com, and this gives you, kind of going up in complexity this way, the number of operations that it takes to solve your algorithm, the elements in there, and so we talked about ON for the sequential search. I'll just kind of go through some of these examples and why they take as long as they do. So let's actually step back a second. How you calculate the big O is you basically, the rule of thumb is you ignore everything but the most complex or intensive calculations, and then you use that as your big O. For example, if we're looking at this bit of code here, you have these two lines where some variables are being assigned. That is just not significant to include in our big O calculation. You have this while loop here that's going to go n times. Now, if that was the only thing in there, then yeah, this would be on. But you have this two nested for loops, which is definitely the most complex and time-consuming part of this algorithm. And so if you follow the rule of thumb, you're going to ignore all this stuff, and thus your big O for this algorithm is simply n squared, because that's the most complex part of it. So that's how that's calculated. So then let's look, though, at some other scenarios in here. And so we talked about O1. That's the quickest solution you can have. That is, here's an example. Here is if you're looking at an array and you only need to look at the first value and to see if it's equal to some value, then really that's one line of code, very quick. Just one operation is performed, and that's all that's ever needed. That's the worst case scenario, and thus the big O is 1. So you're looking at the array, seeing if this spot 0, which is the first spot, is equal to some value. Hopefully that's self-explanatory. So let's look at the next one in this chart. That's ON. So that's this one right here. We'll come back to this one in a second, log n. So ON, we kind of already mentioned that it was the sequential search, where your worst case scenario here is that you go through all the elements and you either find it in the last spot or you don't find it at all. And thus that is n. The complexity is ON. Because the worst case scenario is you looked at all the values. All right, makes sense. So now let's look at n squared. So that is the example I showed you earlier. You know n squared, you have n squared every time you have a nested for loop or while loop that are both of size n. Then that's pretty self-explanatory that you're going to go through that n squared amount of times, right? So insertion sort is an example. Selection sort is actually the same way if you're familiar with your sorting algorithms. All right, so now let's look at the log. So you have these two here that are log n and then n log n. This is probably the part where I see students get the most confused, and it really doesn't have to be. And then let me just describe the notation itself. So you sometimes see log with a subscript. The subscript could be any number. However, 99% of the time, the number is 2. And if you don't see a subscript, it's assumed to be 2. And if you do have a subscript, it'll look like this, log 2 and then n. So what does that mean? So I'm going to just talk about this scenario where it's log subscript 2, since that's, like I said, 99% of the time, that's what you're dealing with. So let's take a look at what that looks like. So it's actually not too complicated. Whatever n is, you keep dividing it by 2 until you get 1 as your answer. Keep track of the amount of times that you divide it by 2, and that's your complexity. So, for example, if n is 50, there's 50 elements in your array, let's say, you would 50 divided by 2, 25, 25 divided by 2, 12, 12 divided by 2, 6, 3, and then you finally get to 1. It took 5 iterations, 5 operations. So if you have an O log n where n is equal to 50, the complexity is 5. So that's the amount of operations it takes. Okay. The best example of that is a binary search, where you just keep halving your data to look for an element. This is a quick, simple example of what log n code would look like, and you see you're just cutting in half x each time, and you go until x is still greater than 0. So you can see that algorithms of this type of nature are very efficient. As the number, as n grows, actually log the complexity, the number of operations, just goes up very minimal. It goes up in inverse exponential. Is the best way to say it. So, all right, so now let's look at n log n. So this is the same as log n, except you run each log n operations. And the best way to kind of show that is right here. So this is kind of the code we had before, where we had this keeps getting halved, but you just run that in a loop n times. So not as efficient as log n, and it's actually n times more complex. Hopefully that makes sense. So I mean, I actually think that if you think about it in terms of that most people just, I guess you just don't realize that the 2 is there by default. And if it was a 10 or something like that, then this would be 10 instead of 2. That's all. Whatever the subscript is, like I said, by default, just assume it's a 2. So I mean, those are the major ones. The 2 to the n, 2 squared n is, you don't come across that one as much. That's more advanced algorithms, and n factorial is even more so. But I'll just give you a quick little definition of that. 2 to the n means that the time will double with each additional element in the list. Examples are recursive algorithms such as the Tower of Hanoi, and that is, you can see you have these 2 different recursive calls, and so as this goes up as n, in this instance top n increases, this gets very time consuming. And factorial even more so. It involves doing a certain operation for all possible elements in the list, and doing that each time that we look at each element. So that is like even more time consuming. Example used to describe that is usually brute force solutions to the traveling salesman problem. If you're not familiar with that, just do a quick search, but that's a very complex algorithm to solve that. I hope that I simplified this. Let me know if you think there's anything that I should add to this, because I do think this is an important concept for computer science students to understand. Thanks for watching. Thanks.